This is part 7 of my lecture on parametric tests for comparing means. In the last part we looked at 2 paired samples, now we're going to look at 2 unpaired samples. When comparing 2 unpaired samples, we're given 2 populations with unknown means, and the data we have available is a sample of measurements from each population, but we don't have any particular pairing like we did with the paired t-test. What we want to do is to test whether both samples could have come from populations with the same mean. The statistical tests available are the 2-sample z-test and the unpaired t-test, and we'll look at each of those. First of all, if we have 2 samples that are unpaired, there may be the same or a different number in each sample. For the paired test, of necessity, we had to have the same number in every sample because they had to be paired 1-to-1. But for an unpaired samples, we may by coincidence have the same number in each sample, but it is not essential to have the same number in each sample because there is no particular pairing between the items. There are 3 cases that we'll look at. First of all, if we know the population standard deviations, we'll use the 2-sample z-test. If we don't know the population standard deviations, but we can assume that both are the same, then we can use the unpaired t-test with equal variances. If we don't know the population standard deviations and they may be different, then we use a different version of the unpaired t-test which assumes unequal variances. So we'll look at all 3 of those in this part. First of all, the 2-sample z-test. Here we know the standard deviations. So we've got 2 samples, size n1 measurements in the first sample and n2 in the other, and they've got means ms1 and ms2 as shown by the 2 samples in the yellow and purple diagram. These are taken from populations with known standard deviations, SP1 and SP2 for the 2 populations. I've not shown those on this diagram to avoid confusion. But the null hypothesis is that both samples came from populations with the same mean. Note we're testing means here, we're not testing the standard deviations. Talk about testing standard deviations in a later lecture. Here we know the standard deviations, all we're doing is testing the means. The test statistic is Z. It's similar to what we've seen before. It's the mean of sample 1 minus the mean of sample 2 divided by the standard error of the difference, SED, where SED is defined as the square root of the standard deviation of population 1 squared divided by n1 plus the standard deviation of population 2 squared divided by n2. Excel can do this calculation using its data analysis tool, so you don't need to worry too much about the details of the calculation. But let's see what it means in practice. SED, the standard error of the difference, is calculated from the standard error of both samples. So the standard error of sample 1, as always, is the standard deviation of sample 1 divided by the square root of n1, the square root of the number in that sample, because as always the standard error is going to be less than the standard deviation, and the more there are in our sample, the smaller the standard error, the more precise our measurement becomes. The same thing is true for standard error 2, being the standard deviation of 2 divided by root n2. And you remember when we were testing for agreement, we showed that we could calculate the standard error of a difference by summing the squares of the standard error of each measurement. So the standard error of the difference squared is the standard error from sample 1 squared plus the standard error from sample 2 squared. And if you put those 2 together, that is why we get the standard error of the difference is the square root of the standard deviation of population 1 divided by n1 plus the standard deviation of population 2 squared divided by n2, and take the square root to get the standard error of the difference. So although it looks a bit complicated, it's actually just the same formula as we saw before when we were testing for agreement. Then the test statistic, as usual, is the difference between the 2 means as a fraction of this standard error of the difference, ms1 minus ms2 over SED. So as always, if the null hypothesis is true, then Z should follow a normal distribution. Notice it's a normal distribution rather than the t-distribution because we have known standard errors. We're not having to estimate them from the data. So we look up the critical value of Z from a table of the standardized normal distribution, and if Z is greater than the critical value, then we can reject the null hypothesis. So that is the Z test. The other test that I mentioned is the unpaired t-test, and this comes in two versions. The first version assumes equal standard deviations. We've got two samples of size n1 and n2 with means ms1 and ms2 and standard deviations ss1 and ss2. They're taken from populations with unknown standard deviations. So we're now assuming that we don't know the standard deviations of the populations, but in this version of the test we assume that both populations have the same standard deviation. The null hypothesis is that both samples come from populations with the same mean, and the test statistic is t, but it's a bit more complicated to calculate. It's still t is ms1 minus ms2 over the standard error of the difference, but we have a rather more complicated way of calculating the standard error of the difference. Standard deviation of the population 1 is estimated from the standard deviation of sample 1, and the same thing for sample 2, and then we calculate a pooled standard deviation and calculate a standard error of the difference from that. That seems very complicated, but don't worry, Excel can do that calculation using its data analysis tool, so you don't even need to stop and think about it. If we do just want to break it down, then we can say that first of all we estimate the population standard deviation from each sample by applying the Bessel's correction. So the estimate of the population standard deviation for sample 1 is taken from the sample 1 standard deviation multiplied by the Bessel correction, root n1 over n1 minus 1, and the same thing for population 2. Then we take a weighted average of the two estimates of population standard deviation to give us a pooled estimate of standard deviation. And you can see here that S pooled squared is a sum of SP1 squared and SP2 squared, each weighted by n1 minus 1, the number in its sample minus 1. Then we take that pooled standard deviation and estimate from that the standard error of the difference by taking root 1 over n1 plus 1 over n2 in the same way as we calculated the standard error of a difference previously. Then the t-statistic is the difference of the means divided by this estimate of the standard error of the difference. And if the null hypothesis is true, then it should follow a t-distribution. T-distribution this time because we've had to use the sample data to estimate the population standard deviation. And the only new thing here is that the number of degrees of freedom is n1 plus n2 minus 2. n1 is the number in sample 1, n2 is the number in sample 2, so n1 plus n2 is the total number of measurements altogether, and minus 2 because we've taken two means in this calculation, the mean of sample 1 and the mean of sample 2. So this is where you have to be careful to know that the number of degrees of freedom is slightly unusual, n1 plus n2 minus 2. The unpaired t-test with different standard deviations is an alternative. We take two sample sizes n1 and n2, means ms1 and ms2, and standard deviation ss1 and ss2, taken from populations with unknown standard deviations, exactly like the previous unpaired t-tests, but this time we assume that both population standard deviations may be different. Last time we assumed they were the same. The null hypothesis is still the same, that both samples come from populations with the same mean. The test statistic is d, difference of the means divided by the standard error of the difference, where the standard error of the difference is determined from the population standard deviation sample 1 and sample 2, each estimated with the Bessel correction from the sample standard deviation. This test is rarely justified. Most of the time you will do the unpaired t-test assuming that they have the same standard deviation, but if you do want to do this, Excel can do it using the data analysis tool. If we want to break it down, then we start as before by applying the Bessel correction to the sample standard deviation to get an estimate of the population standard deviation. Then we calculate the standard error of the difference from the two estimated standard deviations by taking the population 1 standard deviation squared over n1 plus the population 2 standard deviation squared over n2 and take the square root of that. Then the test statistic D is the difference between the means as a fraction of that standard error of the difference. If the null hypothesis is true, then D should follow the t distribution. The trouble is now the number of degrees of freedom gets a bit more complicated. In fact, it's not even a whole number sometimes, which makes it very difficult to look up in tables. But don't worry, Excel can do that calculation for you, so you don't need to worry about the details. If we want to take an example of the unpaired t-test, then let's look again at the intelligence of lecturers, and this time we'll compare them with students. So our question could be, are lecturers more intelligent than their students? The hypothesis is that lecturers have a higher IQ than students, and the null hypothesis is lecturers do not have a higher IQ than their students. Once again, is that one-tailed or two-tailed? Clearly it's one-tailed because we're only postulating that lecturers have a higher IQ than their students, not lower. So we need to acquire some suitable data to try that out. Now, as well as 4 lecturers taking our IQ test, we've also got 5 students taking the same test to measure their IQ. So let's assume we've got some data that the IQ of a sample of 4 lecturers, as we had before, was 110, 104, 114 and 120. And our sample of 5 students gives IQs of 110, 107, 105, 113 and 100. Once again, this is hypothetical data for illustration only. The statistical test we use can be a parametric test because the data are quantitative. We can assume that populations are normally distributed with approximately equal standard deviation because they both come from IQs, and the samples aren't paired because we've got different people in the lecturers and the students group, and they are different numbers anyway, so there's no way we could possibly pair them. So we're going to use the unpaired t-test, and we'll assume equal standard deviations because there's no reason to suppose that the standard deviations are different. Here again is our data displayed. We've already seen the IQ of our 4 lecturers. Here's the IQ of our students on the same scale. Maybe they are slightly lower IQ than the lecturers, but is that significant? That's what we want to test. Notice that there's no pairing. We can't draw lines between these because they're not paired, and there are 5 in one group and 4 in the other, so it wouldn't make sense. We don't do the calculation longhand. Excel can do this very nicely for us. Here we've got a table of the IQs of the 4 lecturers and the 5 students. You tell Excel to calculate that using its data analysis tool, and it comes up with this. It tells you the mean IQ of the lecturers is 112, which we already knew, and the students is 107. It gives the variance as 45.3 and 24.5. There are 4 lecturers and 5 students. It calculates the pooled variance for us according to that complicated formula that I showed you before. That's 33.4. The hypothesized mean difference means that we are assuming in our hypothesis no difference between lecturers and students, so that is the assumption, the assumed difference of 0. 7 degrees of freedom, if you remember, it was n1 plus n2 minus 2. 4 plus 5 is 9, minus 2 is 7. It's calculated the t statistic for us of 1.28. The p-value comes from the significance that we set when we did the t-test. I set an alpha of 0.05, and it says that the critical value for a one-tailed test is 1.89. Clearly our t-value hasn't reached significance. 1.28 is less than 1.89, and it helpfully tells us that the probability of that for a one-tailed test is 0.119, which isn't significant. If we've been doing a two-tailed test, then the critical value would have been 2.36. So you see, you don't actually need to do any calculation yourself. Excel or any other statistics program will do all of the calculation for you, so you don't really need to be frightened by all those complicated formulae. Our conclusion therefore is, for 7 degrees of freedom, a significance level of 0.05 in a one-tailed test, the critical t is 1.89, and we have from Excel of t value of 1.28, so it's not reached significance. So the null hypothesis can't be rejected, so our conclusion is that there is no evidence that lecturers are more intelligent than their students. They may be or may not be, we just don't have enough evidence from this test to say. If you are worried about doing these calculations and you don't fancy using Excel, there are lots of tools available online to do it. For example, some of these websites can do the calculation for you just by typing in the data. At GraphPad you can do a one-sample t-test, or a paired two-sample t-test, or an unpaired two-sample t-test. If you want to use equal standard deviations, that's fine. If you want to do unequal standard deviations, select the Welsh option. At Vassastats, they can do the one-sample t-test and the paired two-sample t-test. They call it independent samples, or an unpaired two-sample t-test, which they call correlated samples. IFA Services will also do a one-sample t-test or an unpaired two-sample t-test, but only assuming equal standard deviations. So you don't have to use Excel, and you certainly don't have to do these calculations by hand. So that's the end of part 7 of this lecture on comparing means.